Hello, my name is Georg Kohl, and in this video I would like to talk to you about our paper Learning Similarity Metrics for Volumetric Simulations with Multiscale CNNs. This was joint work together with my colleagues Li Wei Chen and Niels Thuret. To start, I would like to give a quick motivation and summarize the task that we're trying to solve with this project. So we're looking at the similarity assessment of dense 3D grid data as it occurs from transport or motion-based PDEs. These PDEs tend to be very relevant in the area of fluid flows, for example, for turbulence, liquid or smoke simulations. Common methods to approach this problem are element-wise LP distances, which are inherently problematic as they cannot capture spatial structures or patterns. So for example, if you look at a checkerboard pattern and compare it to another checkerboard pattern which is slided over by one voxel, you get an extremely high element-wise distance, even though the general structure, that they both are a checkerboard pattern, is very, very similar. So to summarize, we would like to utilize deep learning to come up with a robust, physically more meaningful metric that can actually consider these structures. Here, an overview over some related work. As already mentioned, the most common element-wise metrics are the LP distances, but there's also the peak signal-to-noise ratio and the structural similarity index. And then furthermore, there's correlation coefficients that can also be used for a similar approach, for example, the Pearson correlation or Spearman's rank correlation. In previous work, et al. Utilized visual evaluations via user studies for this kind of data, but you can imagine for 3D dense grid data, this tends to be quite difficult, in addition to being slow and expensive. In the domain of images, there's various approaches with different neural network architectures that can solve a similar problem, for example, the ALPIPS metric. Then finally, in a previous paper, we also looked at a learned comparison of scalar 2D PDE data, which is also the basis of this work here. However, we are looking at the more complex case of 3D data and also improve upon various other aspects of this previous work. Here, a quick overview over our method. We start out either with a PDE solver or with a simulation data repository created typically with a PDE solver to create a sequence of volumes. In this case here, you only see a 2D projection, but normally you can assume that these are dense volumes. And we would like to create a sequence of these volumes and order them based on a reference on the left here, and then basically elements with increasing distance to the right. Once we have such a sequence, we can then basically utilize the order of this sequence to come up with pairwise ground truth distances, as we have done in our previous work. But in this case, we actually improved this with an entropy-based similarity model that transforms these ground truth distances so they are more comparable between different systems. Once you have a sequence, we can then basically take pairs of the sequence, feed them into a Siamese neural network, so essentially shared weights. And then in the latent space of this network, we can compare the features of both of these inputs and aggregate the result into a scalar pairwise distance prediction. So once we have the ground truth distances on the left here and the distance prediction on the right, we can then determine a loss and optimize our network to be more accurate and also evaluate how well our network prediction actually matches the ground truth. So in the following, we're going to look at each of these components in a bit more detail. To start with a sequence creation, so on the left here, if we are given a PDE solver, the main idea that we had is you can vary one of your initial conditions of your simulation. So your initial condition is denoted here by Pi, and then you basically change this with increasing steps of a delta value here. And then when you run the simulation several times, you get a sequence of outputs that tends to be less and less similar to the original reference simulation as 0 here. Similarly, if you have a data repository, you can take a cutout around a spatio-temporal starting position P here, and also adjust this cutout position with a spatial-temporal offset. And again, the result is basically a sequence that is decreasingly less and less similar to your original unaltered cutout. And notice that both of these approaches are essentially an iterative process. We added a heuristic there that basically ensures that our sequences are as informative as possible by making basically sure that our values of delta in both of these cases here are not too small but also not too big. So with these two methods, we basically came up with a variety of different data sets. On the left, you can see our training data here. So the most basic is the advection diffusion equation that models the transport of a passive quantity in a velocity field. Then we have the Burgers equation, which also adds a viscosity term to that. And then finally, two instances of the Navier-Stokes equations with a liquid simulation or a smoke simulation here. Then on the right here, you can see our test sets. In the middle here is the Johns Hopkins turbulence database, which we basically made use of as a data repository. And then for the various subsets of this turbulence database, we created some sub-data sets with different flow behavior. Similarly, we utilized the scalar flow dataset on the bottom right here as a source for another test set based on a data repository. Then the top right two simulations are similar to our original training data. However, we add noise to the simulation, so they are sufficiently different from our training data. Then finally, we have a synthetic moving shapes or moving damped waves data set, which is essentially just random shapes moving in a straight line. This tends to be quite difficult for element-wise metrics to clearly distinguish. So next, once we have a sequence, we can then determine a basic ground truth distance similar to what we have done in a previous approach. So if we're given a pair of volumes from our sequence with index I and j, and the sequence actually has length n, then you can see Ws here is our definition of the ground truth distance for this pair, which is essentially just a linearly increasing change over the sequence. However, this does also rely on a highly accurately calibrated sequences, because otherwise the distances from different systems are not necessarily nicely comparable. So as a result, we came up with an entropy-based similarity model that on the one hand compensates for the decorrelation speeds of different systems, so essentially makes sure that the sequences from different systems are comparable, but also takes into consideration that systems tend to initially decorrelate a lot faster and then kind of decorrelate a lot slower. And in a way, we theorize that the similarity should also behave accordingly. So we came up with a logarithmic transformation of our linear ground truth here. And we derived this from the Boltzmann equation. I'm going to skip the details here, but you can look that up in the paper. Essentially, we are taking our linear ground truth, putting this non-linear transformation on top of it, and then getting out more suitable ground truth distances g. The most important thing to look at here is the value of c. This is also visualized in the picture on the right here. Essentially, if the value of c that corresponds to decorrelation speed, if c is very high, then you tend to get a curve like the red curve here, meaning that the system decorrelates very, very quickly, while if the value of c is very small, you get a relatively linear behavior as before. And to basically compute this value of c for each of our sequences, we essentially taking our equation that we came up with up here, and then perform a least squares optimization to find c. We're putting basically a placeholder proxy distance. So the PCC is a proxy distance in this case that allows us to determine c for the system, and then afterwards we can basically apply this transformation to our ground truth distances to come up with a final ground truth that we can then use for training. So once we have the distances and our sequence, we can then basically make use of a fully convolutional Siamese feature extractor network. And you can see the outline of this approach at the bottom here. Essentially, we have a standard convolution plus ReLU block, but we also added that you can actually process the input on various different resolutions, which we found is quite critical, instead of basically just processing it in a single straight line as it is normally done in a CNN. Once we have all of the intermediate feature maps from this multiscale network, we basically then compare them, normalize them, then compare them, and then aggregate them to a single scalar distance. In previous work, we actually also showed that this approach ensures the mathematical properties of a pseudometric. And at that point, it basically is just a supervised learning problem of our ground truth distances with this multiscale model. The loss that we are using in this case, so given the ground truth G and the prediction D, you can see here. Essentially, it consists of a mean squared error term on the left here that directly minimizes the distance deviation. But what we also found to be quite important is the correlation term on the right here. So this is the Pearson correlation, and this is just an inverted correlation term here that essentially takes care of the relative the size of the distances to each other. Because in a way, then you can imagine that we're not only interested in the absolute value of these distances, but also how they relate to each other. And then the two other values here are essentially just weighting factors. To come to the results, we analyzed the generalization of our metric trained on the data as mentioned before, and then we can essentially evaluate how well our predicted distances match to the ground truth via Spearman's rank correlation, where a value closer to 1 indicates a better reconstruction. And you can see that our VolSiM metric at the bottom here quite clearly outperforms the element-wise metrics of MSE or the structural similarity, and even learned metrics like the image-based LPIPS method or our previous approach for 2D data is outperformed by quite a bit. The only cases where it tends to be kind of close, like these here, is where the correlation is already very high and all of the methods tend to be quite accurate. So next, we also looked at transformation invariance, as essentially our metric should be invariant if both of the inputs are scaled or rotated or translated. Since CNN features are, apart from boundary effects or from pooling, already invariant to translation, we mainly analyze the rotation and the scale invariance here by taking 8 random pairs of each of our data sets, rotating them in some increments or scaling them, and then checking how the distances deviate from the mean. This is plotted in the picture on the right here, and ideally a perfect metric that is perfectly invariant would give a distance deviation of 0 across all of these, so essentially a flat line. And as you can see, our proposed metric at the bottom here tends to be quite a bit more stable to rotations as well as scale compared to a non-multiscale approach, which is a standard CNN. So in a way, we find that this means that our feature representation of our network tends to be quite a bit more stable. Finally, we conducted a turbulence case study, which is essentially an analysis of a longer sequence of forced isotropic turbulence, and again, basically evaluating the distance from each of our time steps here along different spans to the first reference frame here. And as you can see, our VolSiM metric tends to match quite well with a established correlation distance that is typically used in turbulence research, even though it was never trained on any turbulence data, and it actually also has to generalize to a larger data size of 128 to the 3 instead of 64 to the 3 in this case here. So to summarize, we can actually learn a robust similarity assessment with our multiscale metric. And the main use cases for this metric are the accuracy assessment of new simulation methods and also guiding generative models, for example, GANs, that can be used to synthesize physical systems. And some future work is a similarity metric that specifically targets turbulence, and also a metric that is scale or rotation invariant by construction, as our approach here only learns this from the data, basically. So with this, thank you very much for your attention. If you want more details, you can have a look at our paper or have a look at our source code in our GitHub repository here, which you can access via the QR code. So thanks for watching.